Hello, this is Roger Cook from Resource for the Future and the TU Delft, doing a little refresher on adding uncertain numbers. And this is to support an elicitation of the contribution to sea level rise from ice sheets to be conducted in the fall of 2025. So let's get started. The first thing to notice is that adding numbers is not the same as adding uncertain numbers. So if x and y are numbers, then x plus y is also a number, and I can compute that number from the numbers x and y. Duh. But the important insight is that if x and y are uncertain, that is to say, are random variables, then x plus y is also uncertain, and its uncertainty cannot generally be computed from the uncertainty of x and the uncertainty of y. Okay, and the best way to think of that is in terms of sampling. So I have this uncertain quantity x, and I can display its cumulative distribution function here, and that has the following interpretation. If I choose a little number, little x, then I compute the cumulative distribution function value at little x, and that is the probability that the random number x is less than or equal to little x. That's what this thing is. So this also tells us how we can sample from the distribution of x. We just go the other way. So I draw a uniform variable on the 0, 1 interval, and I invert this cumulative distribution function, and I get another little x, which is the inverse under f of u. And if I repeat this many, many times with independent samples from the 0, 1 interval, then I will build up the distribution of x. And you might ask, why is this uniform on the 0, 1 interval? Well, think about it. The probability that x is less than its median point, the median value of 50%, that probability is a half. The probability that it's less than its 25th percentile is 25%. The probability that it's less or equal to its 75th percentile is 75%. So these numbers are going to be uniformly distributed. So I can sample from x by sampling a uniform variable and just inverting the cumulative distribution function. This is how we do it. So now suppose I have two uncertain quantities, x and y, and we want to look at the distribution of their sum. Well, to do that, I need two uniform variables, u and v, and I also need the joint distribution of u and v. And this distribution of u and v is called the two-dimensional copula of x and y. And so this is the additional piece of information that we always need if we're going to talk about the uncertainty of x plus y. So in 2009, there was a lovely article in the magazine Wired about the dreaded Gaussian copula which killed your 401ks. A very nice article. It isn't often that mathematics hits the front page, but this is an example. And so I want to explain what exactly he's talking about. So I have here four different copulas. So these are distributions on the unit square which are uniform in the horizontal and vertical margins. This is the Gaussian copula. This is called the Clayton copula or reverse Clayton. This is the Gumbel copula. This is Frank's copula, and there are many, 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 many more. But if we look at this Gaussian copula in detail, we see that the correlation, by the way, these all have correlation 0.8, but here the correlation is sort of smeared out over the whole distribution. There is some contribution in the upper lower corners, but if we look very closely at this upper corner, we see that it's actually tending to the uniform distribution. As I get closer and closer to this corner, it becomes more and more uniform. And that means that the Gaussian copula has tail independence. So if the one variable is known to exceed a very, very high percentile, the other variable tends to be independent of that first variable. If you compare that with the Clayton copula here, you see that that's not the case. In this upper point, it's not tending to become uniform. So the Clayton copula is tail dependent. The Gaussian copula is tail independent. The Frank copula is also tail independent. The Gumbel copula is tail dependent. So one way to think about this is in terms of exceedance probability. Now, this graph is a little bit dense, but I'll try to explain it. If one variable exceeds its 99th percentile, what's the probability that the other variable is going to exceed its 99th percentile? Now, if they are independent, that's going to be, by definition, 1%, right? But if they're not independent, it's going to be something different. So if we look at this Frank's copula, and what I have here are different correlations from 0.2 up to 0.9. And I'm going to consider the case that they are correlated at 0.8. And I want to look at the 99th percentile here. That's here. And I want to look at it on this curve, which corresponds to the correlation 0.8. And so what I see is the following. If y exceeds its 99th percentile, the probability that x will exceed its 99th percentile is about 0.1. Not 0.01, but 0.1. And it's going down to 0. As this 99 goes to 1, this guy goes to 0. For the normal copula, you see a different picture. This is, if I can move myself here, but you get the idea. For the 99th percentile, with correlation 0.8, if y exceeds its 99th percentile, the probability that x will exceed its 99th percentile is 0.4. That's higher, but it's also going to crash down to 0 really quickly as you get higher and higher values. Let's compare that with the Clayton copula and the Gumbel copula. Here you see a very different picture. So if y is above its 99th percentile, and the correlation is 0.8, then you see the probability that x is above its 99th percentile is not 0.1, it's not 0.4, it's 0.8. Very different. And it's not going down. So it stays 0.8 as y goes from its 99th to its 99.9 to 99.999. This guy stays at 0.8. Big difference. And with the Gumbel, it's something similar. So the bottom line is that assuming things are independent is not conservative. So I've made a little sample here of two log normal variables. These are the densities of the two log normal variables, and I'm going to add them. In the first case here, I'm going to add them assuming independence, and I get this density here, right? If I assume they are correlated at 0.8 with the Gaussian copula, I'm going to get this green density here. And if I assume they're correlated at 0.8 with the Clayton copula, I'll get this red one. And so what you see is that the more tail dependence you have, the more these densities, the mode tends to shift down, but the tail gets thicker. And so if I look at the 99th percentile in these two cases, I see if they're independent, the 99th percentile of their sum is 4.61. If they are dependent with correlation 0.8, with the Gaussian copula, the 99th percentile of the sum is 5.75. If I look at the sum with the Clayton copula, also correlated at 0.8, then the 99th percentile of the sum is 5.9, not 5.7, but 5.9. So in any case, you see the biggest effect is to ignore the dependence if it's there. But given that it's there, you also want to think about whether that dependence is concentrated in the tail or spread out over the whole distribution or whatever else. So as you do these elicitations, you want to think as follows. If the accumulation is above its 99th percentile, what's the chance that the runoff will also be above its 99th percentile? what's the chance that discharge will also be above its 99th percentile? And going on, if West Antarctica exceeds its 99th percentile for sea level equivalent contribution, what's the chance that Eastern Antarctica will also exceed its 99th percentile, and that Greenland will also exceed its 99th percentile? So, for example, if you think about what might cause West Antarctica to come up with a very high value, would those things that are driving the high value of West Antarctica also tend to drive a high value for East Antarctica? If so, they are tail dependent. They could go the other way. It might be because of some asymmetries in the whole in the whole climate system, that if the Antarctica goes up, the Greenland goes down. That's also possible. Who knows? Everything is possible. But these are the things you want to think about as you do this elicitation. So I'm going to end by saying good night and good luck. And please think about all these things as you consider the sea level contribution from our various ice sheets. Bye.